Okay, so any questions? Well, there were a couple of missing points in our discussions last week, so I would like to just fill in those first and just make a brief introduction to phase transitions. You see, if you remember what we had done, what we were doing, we are doing this grand canonical ensemble. We said that the probability that the state, our system, will be in a microstate with energy ER and the number of microstates, number of particles ns is given by this expression, where q was equal to sum over all microstates of e to power minus beta er minus mu ns. And we also wrote this as sum over all microstates of z to the power ns e to power minus beta er, z being e to power beta mu. So this we had defined. Then we said, okay, so what is the average number of particles? Okay, the average number of particles is just sum over nr, the number of particles in the given microstates times the probability of that microstate, so which was sum over nr of e to power minus beta mu e minus mu n divided by q, the grand partition function. Then we said, okay, we can also write this as some, okay, so the derivative with respect to mu, well, this derivative will, at constant temperature, I will take the derivative at constant temperature of e to power minus beta e minus mu n. When I take the derivative with respect to mu, it brings a factor beta times n. Beta times n. N is what I want, but there is this additional beta, so I have to cancel that beta, so I can just multiply this by kt. And of course there is this division by the grand partition function. Well, this is also nothing but the grand partition function, so we had the average number of particles was actually kt times the derivative with respect to mu of the logarithm of the grand partition function at constant temperature. Then we were looking at the fluctuations in n. So let me just take the derivative of this average of n with respect to mu. Well, again at constant temperature. Kt times derivative with respect to mu of 1 over q times the derivative of q with respect to mu, which is equal to kt times, well, the derivative of 1 over q is minus the derivative of q with respect to mu, again at constant temperature, times 1 over q squared. Well, there is another derivative. The second term is already there. And then we have plus kt times 1 over q, derivative of the second derivative with respect to mu of q. Again, both derivatives are at constant temperature. Well, you see, the first term is nothing but minus kt times the derivative of q with respect to mu times 1 over q squared plus kt times 1 over q, second derivative of q with respect to mu at constant temperature. So you see, this ratio, this, okay, let me just minus kt. Well, the first derivative, you see, taking the derivative of q with respect to mu just brings down in the exponential factor beta times n. So the first term is nothing but beta and average, and of course we have everything squared. The second term is kt. Again, each derivative with respect to mu will bring down a factor beta n inside my summation. So that is just, I have two derivatives, so it's beta squared times the average of n squared. So this is equal to beta squared kt n squared minus the average of n squared. Yeah, this derivation we had already done in a slightly different way. Now kt cancels one of these betas. This quantity is what we had defined as the fluctuation of n. So basically what we have shown again is that the fluctuation of n around its average is given by kt times the derivative of the average of n with respect to mu at constant temperature. Now, then we said, okay, we are looking at the we are interested in the relative fluctuation. This is equal to kt 1 over n squared derivative of n divided by with respect to mu at constant temperature. Well, then we said, okay, if you look at these, the average of n is an extensive property. N is an extensive property which scales with the size of my system. So basically, mu is an intensive property. It doesn't change with the size. Temperature is an intensive property. It doesn't change with the size of the system. So this ratio, naively, we would expect it to scale as 1 over the volume. And in the thermodynamic limit, it goes to 0. So the fluctuations, we said that, okay, they are negligible. Well, this is true only if the derivatives are finite. You see, if the derivative diverges, we cannot say that this relative fluctuation is 0. Now, let us try to rewrite this expression in a slightly different form. Now, first of all, let me just convert to not the total number, but the number density. Let me define the small n as capital N plus V. Well, I will just avoid the averages just for simplicity. And okay, so that's nice. So the left-hand side now is just small delta n squared over n squared. This is equal to kt over v 1 over n squared times derivative of n with respect to mu. Oh, sorry, this is v, large n is v times small n. Well, although I didn't write it explicitly, all these derivatives are actually also at constant volume. You see, volume enters into our derivation through the expressions of the energies. Energy of the microstate depends on the volume of my system. And when I'm taking the derivatives with respect to mu, I'm assuming that the energy are constant, which basically amounts to saying that the volume is constant. So, okay, so this is our first step. This is kt over v 1 over n squared derivative of n with respect to mu at constant temperature and volume. Well, I will first make a change to the volume per unit per particle. This is V over n, or n is large V over small v. Then the n over d mu at constant temperature and volume is just minus V times derivative of the volume per particle with respect to mu at constant temperature and V times over V squared, small v squared. And so delta n squared, the fluctuation in the number per volume, is now becomes kT minus kT over V, 1 over n squared. Let me see. Okay, fine. 1 over n squared. So here I have no, sorry, I made a mistake over here. No, okay, no. This is capital N, not small n. So this is just 1 over small n. N is 1 over V. So there is no distortion. So here we have 1 over n squared. The derivative is 1 over V squared dV by V mu. Now what I would like to do is I would like to express that derivative with respect to chemical potential in terms of derivative with respect to pressure. That is what I would like to do. Let's just remember some thermodynamic relationships. du is equal to Tds minus Pdv plus mu dn. And so d of u minus Ts plus Pv, which is the Gibbs free energy, is minus sdt plus vdp plus mu dn. Well, you see, this tells me that Gibbs free energy can be written as a function of temperature, pressure, and the number of particles. Well, it's an extensive property, meaning that it should scale with the size of the system. Well, the T doesn't change with the size of the system, P doesn't change with the size of the system. So this has to be equal to, proportional to the number of particles. That's the only possibility, that it will scale with the size of the system. Now, the proportionality constant just turns out to be the chemical potential as a function of temperature and pressure. To verify, just take the derivative of G with respect to N at constant temperature and pressure. This equation tells you that dG by dN at constant temperature and pressure should be equal to mu. So that proportionality constant has to be the mu. Now, if you put it back, dG is equal to dN times mu. This is equal to n times d mu plus mu times dN. This should be equal to minus s times dt plus v times dp plus mu times dN. Well, mu times dNs, they cancel. And then I'm left with d mu is equal to minus s over n dt plus v over n dp, or minus the entropy per particle plus the volume per particle. So let's go back. This is what we had for the fluctuations. Now, at constant temperature, d mu is just vdp. So this tells me that the fluctuation I'm looking for is minus kt over v n squared v squared. There seems to be some mistake over here. We will check in a moment. dv by d mu is just v dp. At constant temperature and volume. Minus kt over v, well, 1 over n squared v squared. There seems to be a mistake, as I said, over here. Just check that. 1 over v dv by dp at constant temperature. Well, this is nothing but the compressibility at constant temperature with a minus sign. It basically measures how much you can compress the system by changing the pressure. You see, if you look at that expression, okay, as I said, there seems to be a mistake over here. Just you can go over the calculation and find the mistake. As expected, it's still 1 over v, so in the thermodynamic limit, it seems to go to 0. But look at that term, dv by derivative, the compressibility. You see, for example, if you look at the phase transition, meaning that, well, let's see, if you have a water at constant, in a constant volume, compressed. So if you just, if you have this such a system, let's assume you have some liquid, some water. There will be water vapor over here on the top. So what you can do is you can try to compress your system. So if you compress your system, what will happen is that the pressure will not increase. Rather, the water vapor will condense. There will be more liquid water and less vapor. So the volume will change, the volume per particle will change, pressure will not change. So in such phase transitions, this kappa T, you see, it's the volume per particle changes, pressure doesn't change, so dP is 0, dV is non-zero, so you divide some non-zero number with 0, you get infinite. So kT diverges. So for such a system, delta n squared over n squared is not finite. Does not necessarily go to 0, so you get large fluctuations in the numbers in your system. Well, you can do a similar treatment for the energy. Well, the treatment is similar, you just need to remember some more thermodynamic properties, and this just turns out to be delta E squared that you would obtain in the canonical distribution, plus some coefficient times delta n squared. So on one hand, the number of particles in your system in a phase transition just oscillates rapidly. If you look at the energy of your system, it is still, okay, there is a canonical fluctuation. The energy fluctuation, you can express it as, well, the fluctuation in the energy, if the system was canonical, well, this is assuming the numbers do not change, plus some fluctuation in the energy due to the number of particle change. Well, that's also kind of expected. The energy might change because there's a heat flow without particle flow, or the particles can be exchanged between various systems. The number delta n squared can be, if the number changes, so it carries with it its energy. So again, close to the phase transitions, delta n squared changes, fluctuates rapidly, so you still have fluctuations in the energy squared. So essentially, okay, whatever distribution ensemble you have, we had discussed the microcanonical ensemble, we had discussed the canonical ensemble, now we are discussing the grand canonical ensemble. Unless you are close to a phase transition, all of them should give you the same result. But close to a phase transitions, where the number of each phase will be changing, there will be a huge fluctuations in the phase, in the number of particles in each phase and the energy in each phase. For such a system, you cannot use the other ones. You have to use the grand canonical. Now let's do kind of an application of this grand canonical ensemble to study the vapor pressure. From what we have already known. Well, in a phase transition, what do we know? We basically have two phases. The liquid, that's just to be specific, it can be any two phases. I mean, it doesn't have to be liquid, gas. But let's just look at liquid and gas phases. Well, the system, I can consider my system to consist of two subsystems. For each one, I can talk about their entropy, and each one I can treat in the grand canonical ensemble, because energy is not constant. Gas phase and the liquid phase, they can constantly exchange particles. Number of particles is also not constant. They can constantly exchange the number of particles. So if we look at the entropy of my system, the first question we should ask is, okay, the entropy is maximized, so what does it tell us? Well, the entropy will be the entropy of let's say, the gas phase. Let's assume that we write the entropy as a function of temperature. We already reached thermal energy equilibrium, meaning that gas and the liquid phase already have some common temperature. The numbers might be fluctuating, let's say Ng. Then we have the liquid at the temperature T and the number of particles NL, and the number of particles in liquid. Well, we know that Ng plus NL should be equal to N, which is constant. The total number is constant. It's either in the liquid phase or the gas phase. Well, let's see how the entropy changes. ds will be dsg by dng plus dsl by dnl times derivative of the number of the liquid particles with respect to the number of gas particles. Well, since this is the total number is constant, I can write the total entropy as a function of the number of gas particles, because the number of particles in the liquid phase is already fixed by the total number, which is constant, and the number of particles in the gas phase. Well, this is -1. So this is equal to del Sg by del Ng minus del Sl by dNl, and when it reaches equilibrium, this should be 0. The entropy is no longer changing in equilibrium. It had already reached the maximum. Well, what is the derivative of entropy with respect to N? Let's remember du is equal to TdS minus PdV plus mu dN. Or ds is equal to 1 over T du plus P over T dV minus mu over T dN. So the derivative of the entropy with respect to the number is just minus the chemical potential over T. Minus mu G over T, Tg. The temperature of the gas phase, we already assumed that it is the equal, plus mu L over T dN should be equal to 0. Oh, not dN. The chemical potential of the gas phase and the liquid phase, they should be equal. This is the condition we have for equilibrium between different phases. Now, we had already looked at some simple models of the gas and for the liquids or solids. For gases, yes, if it's sufficiently diluted, we know that the grand canonical partition function was written as z to the n q1 to the power n over n factorial, or e to the power z q1. And then we said that if they are sufficiently diluted, q1 will, the partition, canonical partition function for a single particle will be proportional to volume with some function that depends only on the temperature. So the grand partition function of the whole system, its logarithm is just z times v times f of t. Or, and keep in mind that the logarithm of q, do you remember what it was? PV over KT. So Z, and if it was sufficiently diluted, we also had shown that this is equal to N. So Z times the volume of the gas phase times f of t is equal to the number of particles in the gas phase. Or z of the gas phase is the number of particles in the gas phase divided by the volume of the gas phase times 1 over f of t. And then we had a simple model of a solid. So we are looking at the we said that for solids, Q will be equal to Z to the N, Q to the N. Well, a simple model for the solid is just a collection of harmonic oscillators. So this is equal to Z to the N times Q1 to the power N. A system of harmonic oscillators are distinguishable, so we don't have that N factorial. So Q is just 1 over 1 minus Z times Q1. Well, logarithm of Q1, logarithm of Q is minus the logarithm of 1 minus Z of Q1, which should be PV over KT. N, let's calculate the N. If you remember, N was KT times the derivative of the logarithm of Q with respect to mu at constant temperature. This is equal to KT. Derivative of this logarithm with respect to mu is, well, only Z depends on mu. So we can write it in terms of the derivative of the logarithm with respect to Z, that is Q1 minus Q1 over, there's a minus over here, 1 minus Z Q1 times the derivative of Z with respect to mu, which is derivative of Z with respect to mu is just beta times Z. So N is just, this minus cancels this minus sign. This beta will cancel this KT. N is Z times Q1 divided by 1 minus Z times Q1. And which tells us that we can solve for Z, ZQ1, Well, ZQ1 is equal to n minus ZQ1 times n, or ZQ1 is equal to n over 1 plus n, which is 1 minus 1 over n. Now, what is Q1? Well, in the case of the free particle, we said that it has to be proportional to the volume, because the particle can be anywhere in our volume. Well, in this case, the harmonic oscillator is fixed, so it cannot depend on the volume. It can only depend on the temperature. This is just a function of temperature. So Z of the solid just becomes a number of particles in the solid phase, 1 plus number of particles in the solid phase, times 1 over phi of t. Or this is equal to 1 minus 1 over the number of solid particles This is for the Z. Or let's just 1 over phi of t. Well, we know what happens in equilibrium, in solid gas equilibrium. Well, this is also sometimes called sublimation. Not under all conditions a solid should melt first and then become a gas. It can just directly make a phase transition to a gas. In such an equilibrium, the condition is, let's say we have the Z for the gas, Ng over Vg. This should be equal to 1 over phi of t. Well, most of the time the volume of the solid is negligible. So Vg is approximately the total volume of the system. So the number of particles in the gas phase is just V times f of t over phi of t. So once you know what these f of t and phi of t are, then you can determine the number of particles in the solid phase, in the gas phase, sorry. Now the question was the pressure. You see, the pressure was given by is PV over KT is the logarithm of Q. And logarithm of Q for the gas is Z times V times f of t. And Z, well, let's see, this tells me that the pressure of the gas is, well, the V's, they can cancel, I can cancel the V's, so we get the Z of the gas times KT times f of t. Or if you like, this is KT times f of t divided by phi of t, because Z of the gas should be equal to the Z of the liquid, and Z of the liquid is just 1 over phi of t. So again, if you know the temperature and the F and G, you can determine the pressure of the gas in this gas-solid equilibrium. And the condition for the existence of such an equilibrium is actually given by this relation over here. This should be less than the total number of particles you have. And the critical temperature at which you have this liquid phase transition, can be determined by the condition at critical temperature. Here you have an equality. So at this temperature, you start to have gas-liquid phase. If you are above this temperature, then all of it will be gas, will be converted into gas. Any questions?
Can we use this relation if we have temperature above the critical?
Here I started by assuming that there is a solid-gas equilibrium. Mm-hmm. And that equilibrium exists only below this temperature. Above this temperature, these relationships are not valid. So because this assumes that if you, for example, change the volume, the solid will evaporate. Or if you compress the volume, the gas will become solid. If this doesn't hold, these relationships will not hold. But basically, if you know the thermodynamic properties of the solids, that means you know phi. If you know the thermodynamic properties of the gas, that means you know F. You can determine the vapor pressure above your solid. Well, we didn't look at the solid because to model the solid, it will be more liquids or it will be more complicated. But even a liquid can be done. For a liquid, it will you cannot ignore the interactions between the particles. That will be the main problem, main obstacle. In a solid, you can model those interactions by assuming that they are just doing small vibrations around their equilibrium. So in that sense, solids are simpler. Gases are simple. Liquid would be the most complicated phase. Okay, so I will end today's lecture here. Tomorrow we will be discussing more generally what's a phase transition, and then, if we have time, we will probably start the quantum statistics. So, up to here we have used some simple applications of quantum mechanics, some quantum mechanical systems, but nevertheless we will just delve deeply into the formalism and some more significant applications, especially at low temperatures. So all the systems that we had studied here, even when we were taking into account the quantum mechanical effects, we were still assuming that we are at high temperatures, so that not more than one particle occupies a given quantum mechanical state. So we will try to remove that approximation. And I'm also waiting for your second homework this week. So that's why I will not be giving you a third homework. And we were just, in fact, discussing when to have the midterm. So we had said that, okay, maybe next Thursday, you will have your midterm. Okay, I arrive here around 8:45. So, the moment you arrive, if you arrive early, you can start early. And you will have time up to noon in classroom. Well, I will just announce the room. So next Thursday is 12. Okay, so see you tomorrow.